What should I watch tonight? Do you ever ask yourself that question? What if I told you that our project can give you an answer to that quickly? This is our project on movie recommendations using machine learning. What's the problem? There are thousands of movies out there, and it could be hard for users to know what to watch next. People want recommendations that match their personal tastes. By using some models, we can predict how much a user might like a new movie by giving it a rating from 1 to 5. This helps suggest a list of movies they are more likely to enjoy. With so much digital content available today, recommendation systems are important for keeping users happy. Platforms like Netflix, Hulu, and Amazon use these systems to suggest content users will enjoy. Building a good model rating predictor helps these systems know what each person might like. Better predictions mean people can find great content more easily, stay on the platform longer, and have a more personalized experience overall. These are the three models. 1. XGBoost uses gradient boosting to predict outcomes with impressive accuracy. In our case, it predicts the rating a user would give to a movie based on features like genre or past behavior. 2. Weighted K nearest neighbors. This one looks at a user similar to you and guesses what you might like based on what they liked, and it's weighted so your closest neighbors have more say. 3. Matrix factorization breaks down our giant user movie rating matrix into 3 parts. Together, they help us find patterns we didn't know existed. So, yes, these are our little friends, small in name, mighty in predictive power. The movie dataset is our tribute. It contains thousands of user ratings, movie titles, genres, and more. This gives us everything we need to understand what people like, what they really don't, and how to make smarter recommendations. So here's we've got 3 things that are related to our movie recommendation system. First, Spotify music recommendation. Same concept, different medium. Instead of movies, it's music. Then we got the Amazon movie reviews dataset, tons of user opinions that help us understand what makes a movie likable or not. And finally, logistic regression, a classic algorithm used in other recommendation systems. Not what we use, but it's similar, solid, and still gets the job done.
So in data pre-processing section, we first started by data reduction, feature selection, and data integration. We use the files ratings, modes, and movies. We join both files using movie ID to combine rating with movies details such as title, genres, release date, and vote average. We also removed rows with missing values, made sure all formats matched. Second, we applied normalization for different columns like popularity and vote code, vote average. They had different scales. We applied normalization to help the model treat each feature equally when learning. Third, we did data validation. We use all the attributes. We split it 80% for training, 20 for validation. This helps us evaluate how well our model will perform on new data. Then we use one-hot encoding for the genres attribute. So genres are text, example action, drama, comedy. So we applied one-hot encoding. Each genre became a separate binary column. So 1 if the movie has that genre, 0 if it does not have it. Lastly, we did attribute extraction. For the release date, we extracted the year from the full date. This helps us reduce complexity. Matching learning models work better with simple inputs. So, in short, we cleaned and prepared all the data using the pre-processing steps and made it ready for our models to work.
Data exploration. Within the statistics, we see many variable sections. The count row, which takes the number of entries for all of the movies. The mean row, which takes the average value of each column within each of the columns. The STD row, which is known as the standard deviation, indicates the spread of the values. The minimum signifies the minimum value in each column. The first quartile, which contains the lowest 25% of data for each column. The median is the middle value for all the data in each column. The third quartile contains the top 25% of data for each column, and the max is the maximum value of data in each column. Statistics for these helps us understand how the data is spread out, and using the shows, it gives us the average rating, the ratings variation, and the highest and lowest values.
Another thing we did with data exploration were histograms, and we can see each histogram we used a smooth kernel density estimation curve to enhance visualization. Here we have the distribution of the rating. You can see the most common rating is 4. Here we have the distribution of the vote average. We can see that most of the vote is around the vote average is around 7. And you can also see here with the distribution of the popularity. Popularity is mainly between 0 and 10. You can see during the lease year that most movies in the data set are between the year 2000 and 2010. And the distribution of the vote count, we can see most of the vote count is below 400. And then we also use a correlation matrix to show that the correlation, we have a moderately positive correlation between vote count and popularity with a correlation coefficient of 0.736. And this implies that the more people view a movie, the more likely they are to participate in a vote regarding it. All right, and then we also did a PCA dimension reduction where we reduced 5 dimensions: popularity, vote average, vote count, rating, and release year to 3. And we did that. And this is the explained variance ratio. So each principal component, that's the percentage of the variance out of the entire data set. The ratio of the variance that it explains from the entire data set. And then we chose 3 dimensions because again it has there's good visualization, and there's also a high, it expresses over 80% of the explained variance of the data set. See, with 2 we only get 65%. So since the cumulative explained rate variance is so high, it's a good dimension to reduce to because we contain most of the variance in the data set.
Now let's dive into our model training, testing, and validation. Ever spend more time picking a movie than actually watching one? Can machines help us pick the right movie faster? Yes, we can build a recommender system to do that using matrix factorization, more specifically, singular value decomposition. Matrix factorization breaks down taste by using what you have already rated. From our dataset, we built a ratings matrix. We created a user movie matrix with ratings as the cells. But wait, it's mostly empty. It's sparse. What if we could fill in these blanks? That's where SVD comes in. So here's the magic behind movie recommendations. Singular value decomposition, or also known as SVD. It sounds intense, but it's just math playing matchmaker. We start with the ratings matrix, users as rows, movies as columns, and the ratings they have given. But most of it is empty, because no one has time to rate every movie ever made. SVD breaks that big sparse matrix into 3 smaller ones. Here you see the equation. U is an orthogonal matrix that is all about the users, what kinds of movies they tend to like. Sigma is a diagonal matrix that tells us which patterns matter most. V transpose is also an orthogonal matrix that breaks down the movies by hidden features. So instead of relying on explicit ratings, we're uncovering latent preferences. We learned that even if a user hasn't seen a movie, they might still love it because your taste aligns with its hidden ingredients. On the slide, you see that visualized. One matrix connecting users to genres and another connecting genres to movies. It's like decoding taste buds with algebra. And now, that's how Netflix knows what to recommend, even when you swore you were just watching one episode. So how smart is our model? Well, it's not a mind reader, but it's doing pretty well. We use SVD for our model and we're evaluating it with two metrics. Root mean square error tells us how close the predicted ratings are to the actual ones. Ours is 0.89, which lands us in the good zone. Then there's recall, which checks how often we successfully recommend movies the user actually liked. We got 0.84, also in the good range. So no, it won't recommend your soulmate, but it will recommend a movie that'll keep you entertained. And that's close enough, right? Let's zoom in on one user. We see what they actually loved and what our model thinks they would. Let's look at user 28. First, we've got their actual rated movies, and I have to say, I kind of like their taste. They gave 5 stars to Ghost Rider and Rush Hour. Now on the right, we've got what the model recommended. Sleepless in Seattle, Straw Dogs, Scarface. I know Scarface, but the others, not so much. I have to look them up later. Looking at the genres though, things start to make sense. There's drama, action, and some thrillers, which is right in the line with user 28's style. They are into action and drama-heavy movies, and the model is doing a pretty good job suggesting similar genres. So overall, it looks like the system's on the right track with its recommendations, though there's a mix of familiar and new titles in there. But what do you guys think?
So our second model we went was XG Post. Because our data was kind of messy, it had numbers, text, lists, even some missing stuff. XG Post is really good at handling all that. It uses decision trees, little ifs and logic steps, and builds a bunch of them to learn from the data. It's also fast, flexible, and actually used in a lot of real world machine learning, which made it a great fit for predicting movies rating where different features all interact in complicated way. So how XG both make predictions? We give it features like genre, budget, popularity, user, average rate. Then it builds a bunch of small trees. Each tree asks a few small questions like if some movie is action, go left. If popularity is more than 11.5, go right, and so on. So each tree gives a tiny vote, and all those votes end up adding up to a final prediction. So instead of just saying 4 stars blindly, it's kind of like based on everything I have learned, this one feels like 4.2. Now, XG Post was really solid in predicting 3 and 4 as it's in the confusion matrix. But the model kind of avoided the extremes. It never predicted 1 star and it missed a few 5 stars movies too. It's like it was too afraid to say something was either amazing or terrible. It just stayed in the comfort zone. So we saw some over smoothing, but it definitely picked up on the general trends. In the end, we got a root mean squared of 0.9106, which means our prediction were less than 1 star of on average. That's pretty solid, especially for our data set this complex. And while the model wasn't perfect, it gave us consistently reasonable prediction across a wide variety of movies and users.
So the third model that we used was the weighted KNN. So the traditional KNN, which is K nearest neighbors algorithm, finds K nearest data points or neighbors to a query point and makes a prediction, which is a majority vote for classification or average for regression. The weighted KNN algorithm assigns a weight to each of the K neighbors based on their distance to the query point, and closer neighbors get higher weights. So basically, KNN often improves performance over the traditional KNN because it more intelligently reflects the idea that closer neighbors are more relevant than farther neighbors. And usually, in this case, a very popular weighting scheme is the weight is equal to 1 over the distance from the query point to the training instance. And using the weighted KNN leads to more localized predictions, predictions that are more responsive to fine-grained patterns, and it reduces the influence of outliers or noisy data points. And this is beneficial to us because we're working with real-world noisy data sets, which is not uniformly distributed, or the features can be non-linear, so it provides more accuracy for this type of data set. So for the training and the testing, what we did was we used a grid search to determine the optimal k parameter. So basically this determines which k parameter, which is the number of neighbors you should consider around each query point, it provides the highest accuracy of classification, right? Or, yeah. So in this case, it told us that the optimal k was 32, and we used the k-fold cross-validation scheme. We used 10 folds. So basically how this works is, model trains 9 out of the 10 folds. It divides the data set into 10 folds, it trains 9 out of the 10 folds. It evaluates, it's evaluated on the remaining fold. And then this repeats across each of the 10 folds until all 10 folds are evaluated. So and then we use the MAE and the MSE to measure error. So the MAE is the mean absolute error. It's easier to understand. It's the average of the absolute differences between predicted and actual values. So it tells you on average how far off your predictions are from the actual value. And then we also use the mean square error because it squares the errors and it penalizes large errors more than smaller ones. So it's useful when there are large deviations from the true value. So these are the two most relevant, most useful error measures. Performance and results. We obtained an average absolute mean error across folds of 0.7685, average mean squared error across folds of 0.97, pretty accurate, pretty low error. And then we took 10 random samples of predicted versus actual values, and these are the folds they're in, and we can see the actual rating and the predicted rating right there. Pretty close. And there's some more insightful visuals. Here we can see the MAE and MSE across the folds. So these are the average errors across each fold over all the validation schemes after each run, and we take the average of all of these averages to get these average error values. So that's the progression. So that explains how we determine that. And then we also have the distribution of errors here. So we have the actual minus the predicted ratings, and we can see that it's a pretty normal distribution, and the error, the mean of that, is centered around 0. So most of our error is very low. So that's very good. So that shows a very low error and very high accuracy of the model.
The summary. Why this matters. This isn't just an academic. The models power your playlist, your shopping carts, and even your YouTube rabbit holes. They decide on what you click next. By training a simple SVD model, a KN, and a XG boost, we may taste mathematical. Machine learning allows us to realize that it's not just movie recommendations that are being random, but it's actually being personalized for us. Using XGBoost, weighted KNNs, and matrix factorization allows us to evaluate how effective our training data was in predicting the recommendations. In our matrix, our RMSE was 0.89687. In XGBoost, our RMSE was 0.9106. And in the weighted KN, our optimal K was 32 with a 10-fold cross-validation, with our MSC being 0.97 and MIE being 0.7686. Our reference resources are listed as below, and with our appendix, being able to follow through on details with the data sources, pre-processing steps, exploratory data analysis, and modeling techniques are the main usages within the project that highlights their contributions to improving movie recommendation accuracy. And this is the end.